we will discuss about Coulomb's inverse square law. Coulomb is the scientist who experimentally found a relation between the force acting between the charges and the magnitude of the charges present on the bodies and separation between the charged bodies. We may consider a charge to be a point charge if its linear size is much smaller than the distances considered. Let us suppose there are 2 point charges, say Q1 and Q2, and suppose there is a separation, say some R. Then he experimentally observed using what is known as torsion balance. This is the balance which is used in determining the gravitational constant by Cavendish in gravitation. That is what you studied in first year. So similarly used charged bodies and found that when the charges are halved, keeping the distance same, the force between them became 1/4. Similarly, when the distance is halved, force became 4 times. So that experimental observations mathematically can be written as force is proportional to the product of the charges directly and inversely proportional to the square of the distance. Hence we can write the equation like this: A into Q1 Q2 by R square. So we take the positive value, modulus value. Now the constant of proportionality is arbitrary, so we can choose any value of k. So depending upon the value of k chosen, the unit of charge changes. So in SI units, to define the unit charge, they took the value of this k as 9 into 10 to the power of 9. So if you take the value of k like this, so for a charge of say 1 unit, which is called as 1 coulomb, for a separation of 1 meter in vacuum, the force acting to charges will be 9 into 10 to the power of 9 newtons. So if a force of this much acts between 2 positive charges, they repel each other with this force if they are separated by a distance of 1 meter in vacuum. So 2 point charges of equal magnitude, which are positive charges, separated in vacuum by a distance of 1 meter, if experience this much of force, the charge on the bodies is said to be 1 coulomb. Actually, the unit of coulomb is to be defined in terms of electric current. So, if 1 ampere current passes through a point in a conductor, in 1 second, the quantity of charge flow is taken as 1 coulomb. So, that we will discuss in current electricity. Okay. Now, in SI units, the force formula is actually written as 1 by 4 by epsilon naught Q1 Q2 by R square. For the sake of convenience, they defined a quantity called epsilon naught, which is nothing but permittivity. We call that permittivity. So this is permittivity of free space whose value is given by 8.854 into 10 to the power minus 12 Coulomb square per Newton per meter square. So this is the unit of this epsilon naught called as permittivity. So this is defined for the convenience of defining unit of charge, that is coulomb, and when the medium changes, actually this value changes. That we will discuss later when we discuss about dielectrics. Okay. Now, since force is a vector quantity, the equation of the force is to be expressed in vector notation. For that, what we do is we do something like this. So let us suppose these 2 charges from the origin. So this Q1 is having a position vector of R1 bar and the position vector of Q2 is say some R2 bar. Since these two are similar charges, they experience a repulsive force. Now, if you consider the force on the second point charge due to the first one, we say the distance from the first charge to the second charge, so R21 bar. Now, we write the force on the second charge due to the first charge like this. F21 bar is equal to 1 by 4 pi epsilon naught Q1 Q2 by R21 square. We put one unit vector in the direction of the R21 bar. So you choose unit vector in the direction of this R21 bar. Then that we can call it as vector rotation of Coulomb's law of force acting on the charge 2 due to 1. Similarly, we can write, and here this R21 bar is nothing but R2 bar minus R1 bar. Okay. Similarly, the force on the first charge due to the second one can be written just by changing the letters 1, 2. If you interchange them, so you will get the equation for the force acting on the first charge due to the second one, that is F12 bar, and here it is F21. So therefore 1 by 4 pi epsilon naught Q1 Q2 by R12 square. So here the unit vector is written as like this. So this is just nothing but just reverse the direction. All the magnitude remains the same. Only thing is the direction is reversed. Hence you can write like this, minus F21 bar. So it means if the force on a charge is said to be action, the force on the other charge must be taken as reaction. This is in accordance with Newton's third law. So the forces acting between the charges are mutual. If a charge exerts a force on one charge, an equal force acts on the first charge also in the opposite direction. Suppose if you have a system of charges, how to find out the resultant force? That is, suppose you have number of charges in a region. Find charges. So say suppose this is Q1, here it says some Q2, here it says some Q3, and so on. Now I want to find out on Q3 what is the resultant force. So all are considered to be similar. So due to Q1 on Q3, a force say F31 bar acts like this. And similarly, due to this Q2, a force on 3 acts like this, F32. So, one thing you should know that the force between the charges acts along the line joining the center of the charges. So, therefore, we draw the arrow in the direction of the line joining the centers. So, this is if on the third charge 4 due to 1 is acting like this. So on 3 due to 1, on 3 due to 2. So the resultant is obtained by using parallelogram law of vectors. So construct the parallelogram. This gives the resultant force. So we write like this: resultant force on the third charge is F31 bar plus F32 bar. So, like that, for any number of charges, you can find out the resultant force by using parallelogram law of vectors or law of addition of vectors. So, here one thing you should remember: the force on a charge is independent of, between two charges, suppose, is independent of the presence of the other charge. So, it behaves as if the other charges are not present. So, for a system of charges, if you are calculating the force on a charge, you have to consider force due to each charge separately and then find out the resultant by using vector addition. So it means that the force on a a charge due to the other charges, or due to a charge is independent of the presence of other charges. So in this way, we can write in general like this. This is equal to 1 by 4 pi epsilon is common. Then we can put a sigma sign. So that is Q1 Q2 by. Generally we say if the distance from the first to the second one is R21 square. So since you have taken the sigma sign, so you like such pairs of charges, you calculate the force and then find the resultant using vector addition. So this is how we calculate the resultant force due to a system of charges. Now we will go to another topic, that is electric field. So what is electric field? What is its significance? That we will discuss. Electric field. So electric field is a concept developed by Faraday in order to explain action at a distance. We have seen that charges are exerting forces. Suppose if there is only one charge, then what happens to the force at a point? Will it be there or not? So, in order to explain this, Faraday introduced the concept of field. Suppose you have a charge Q. Now, from this charge, you keep another charge at some distance R. Then, if you keep some small charge Q, it will experience a force, and you know that is given by the Coulomb's inverse square law. Now, if you remove this charge Q at that point, so what will happen? So the field will be there. You can experience that field by the force experienced by the charge if you keep that charge there. So hence we call this charge as the test charge. So electric field is the region around a charge in which at any point the force due to this charge can be felt. So I can write this electric field strength like this. Electric field strength E1 is equal to 1 by 4 pi epsilon naught Q by R square. So of course, since electric force is a vector, so what I have done, in the place I have removed this Q there at that point, even then the force must be there. So I have taken this position vector R bar. So I took the magnitude and I multiplied with the unit vector in that direction. Therefore, generally we can write force on the charge Q is given by Q times this electric vector. This is electric field vector. Or we can write like this: 1 by 4 pi epsilon naught capital Q small q by R square to R bar. Something like that. So, since electric force is a vector, electric field also must be a vector. So, in order to explain the concept of action at a distance, actually they are not moving, they are not in contact, but this charge is experiencing this. But one thing here you must keep it in mind, that is the presence of this test charge should not change the position of the actual charge capital Q. That means Q should be very, very small. Then what happens? The force acting between the charges also decreases. That means if Q is small, naturally F is also small. So we take very small value of Q such that it will not affect the capital Q charge. So its position not altered, not changing. So therefore, if the charge you have taken is very small, then force is also very small. But this quantity is finite. So that is force per unit charge. This quantity must be finite. So very small values you have taken. These two are very small, but that ratio is not that very small. It has some finite value. Hence, electric field is defined as the limit of F by Q as the Q value tends to very small value, that is 0. So, actually electric field strength is defined in the limiting case like this. Now, what is the significance of this electric field? Means actually to discuss the electric forces between the charges in static condition, the field concept is not necessary. Its importance lies when the charges are in accelerated motion. For example, if these charges Q1 and Q2 are in accelerated motion, then if Q1 exerts a force Q2, it won't receive that force instantaneously because it has to send some signal to that Q2. We know that any wave or any signal in vacuum can travel with greatest velocity, that is the maximum velocity with which a wave or a wave can travel, that is a signal can travel, is the speed of light in vacuum. So it will take some finite time for the signal to reach from the charge Q1 to Q2. So here Q1 is the cause and the effect is on Q2 because it experiences a force. So there is a time delay between the cause and effect. So in order to explain this, it was done like this. Whenever the charges are in accelerated motion, or you can say whenever the electric field changes with time. So time varying electric field. Similarly, we can apply it to magnetic field. So actually, whenever electric field varies in the surroundings, magnetic field also varies. You are going to learn about this in later chapters. So it is actually the electromagnetic field if it is changing with time. So if there is a time varying electromagnetic field, then electromagnetic waves travel through the space and reach from one charge to another charge and exert a force. That means they carry energy. Electromagnetic signals or waves in the form of field variations carry energy with the speed of light. It was experimentally found also. So that is where the electric field concept becomes more important. Whereas when the field is static, it is just nothing. It is not required to apply the field concept for calculation of the forces. Therefore, its importance lies only when the charges are in motion or when there is a time varying electric and magnetic field. Okay, so the unit of electric field strength can be easily found from this. It is Newton per Coulomb, and in later chapters you are going to know that volt per meter is also another unit of electric field strength. And you know, electric field is a vector. So here you have taken one charge, the other test charge is Q. But if there are a system of charges in a region, so suppose several charges are there, then the resultant electric field is given by, as in case of electric force, you will be writing it like this: E1 bar plus E2 bar plus and so on. So in that way, by vector method, you can calculate the net electric field due to a system of charges. So your formula becomes 1 by 4 pi epsilon naught sigma Q1 by R1 square and so on. So like this. So you can put the R1 cap and you can continue that. So in that way, you can find out the electric field strength. So electric field strength is also depending inversely on the square of the distance from the point. Okay, and from the concept of solid angle, that can be explained. Now we will go to electric field lines concept. We will discuss about the concept of electric field lines. See, in order to get a pictorial view, instead of using some mathematical methods, so to get a pictorial view of the field, the concept of field lines is introduced. According to this, we can draw lines around any electrical charge, as you know about magnetic lines. Here, it was actually told by Faraday that they are magnetic, they are electric lines of force. But instead of calling it, we follow the word, we use the word field lines. Instead of force lines, we use the field lines. Here, suppose you have a point positive charge. The field lines are considered to be radially outwards. Actually, why it is taken radially outwards can be understood only if you know the concept of potential. So you are going to learn that in the direction in which the electric potential due to a charge decreases at the maximum rate, that is taken as the direction of the electric field. This you will understand in later chapter or in the next chapter. And if it is a point negative charge, the electric field lines are considered to be radially inverse. Okay, see, actually the electric field line is a curve in an electric field. At any point, the tangent drawn gives the direction of the electric field at that point. So that is the actual definition of electric field line. That is, the electric field line is lines are curves in an electric field in which the tangent drawn at any point gives the direction of the electric field. So for a positive charge, this is the concept we use. For a field due to negative charge, this is the concept we use. Suppose you have two positive charges or similar charges nearby. The field lines are like this, something like that, repulsion, like this. Similarly, you can draw for negative charges. Suppose you have an electric dipole having both positive charge and negative charge separated by some distance, then the field lines are like this. Here the curves start from the positive charge and end at negative charge. So the important properties of field lines are this. One is the definition of electric field. That is, the tangent drawn at any point on the electric field line will give the direction of the electric field at that point. And the second one is, the electric field lines are actually not closed curves. They are continuous. But in the case of an electric dipole, they start from positive charge and end at negative charge. In the case of isolated charges, the electric field lines, in the case of isolated positive charge, the field lines are radially outwards and go up to infinity. And in the case of point negative charge, they are radially inward, they come from infinity and end at the negative charge. The third point is, electric field lines never intersect, because if they intersect at the point of intersection, the field must have two different directions, which is not possible. And another point is, wherever the field lines are known, there the field strength will be greater. So the number of field lines gives an idea of the strength of the electric field. Greater the strength, greater will be the number of field lines passing through the space. Another important point is electric field strength. Actually, let us suppose, if you imagine a point charge at every point on a sphere, whose center there is a positive charge, the field is same. So the field direction is radially outwards. This is like this. The total number of field lines you can draw may be many, but whether you imagine a large sphere or a small sphere, or irrespective of the surface area or surface area you are considering around the charge, the number of field lines will remain same. But the intensity of the field you will observe here. Suppose same area you consider here. You may have less number of field lines going through this. So as the distance increases, the field strength also decreases. But through the whole enclosed surface, the total number of field lines passing through will be same. And another point regarding the electric field is, electric field due to a point charge has spherical symmetry. That means at every point at equal distance, field strength is same. So that is in 3 dimensions. We can imagine a sphere. At every point on the sphere, equal distance from the center, field strength is same. So that is called as the spherical symmetry for the electric field strength due to a point charge at the center. Now, so these are the characteristics of electric field. So the important point is, electric field is a concept, the field lines is a concept, and from definition, it is the tangent, it is the curved line in the electric field. The tangent line at any point must be the direction of the electric field. The electric field lines will never intersect. If they intersect, the field must have 2 different directions, which is absurd. Another point is, from a point positive charge, the field lines are radially outwards. From a point negative charge, the field lines are radially inwards. And in case of a dipole, the field lines start from positive charge and end at negative charge. And these are some important points regarding the electric field lines. Okay. So in the next class, we will discuss about the electric flux and about electric dipole, and we will calculate the field strength due to the dipole.